Okay, so these are examples of the types of problems that you'll have for your homework assignment. So the first group, you are given two pieces of information and asked to find the remaining trigonometric functions. So here's an example. So you're given the tangent of x equals the square root of 3 over 3, and that the cosine of x equals minus the square root of 3 over 2. So these are one of those main angles. One thing you can think about here is we may not need it for the solution of the problem, but let's just think about where we are here. Which quadrant does this apply to? So we have the tangent of x is positive and the cosine of x is negative. So all students take calculus, and if we do the tangent of x, that's first, it's positive in the first and third quadrants, and the cosine of x is positive in the first and the fourth quadrants, and therefore it's negative in the other ones. So that's kind of my abbreviated table. So for the tangent to be greater than 0, that's the first and the third quadrant, and the cosine is less than 0 in the second and third quadrant. So the one that's common here is the third quadrant. So this is a third quadrant situation, like that. But you can use some of these trig identities to figure out the other trig functions. So the reciprocal ones are the easiest ones. So the cotangent of x, which is 1 over the tangent of x. So instead of the square root of 3 over 3, you get 3 divided by the square root of 3. But we multiply and divide by the square root of 3. So in the numerator we get the square root of 3 times the square root of 3, and the denominator we get 3, and the 3's cancel out, and we just end up with the square root of 3. So that's the cotangent using the reciprocal identity. Likewise, the cosine is the reciprocal of the secant, or the secant is the reciprocal of the cosine. So there we take the numerator and the denominator and switch those around. Again, we multiply and divide by the square root of 3. So we get negative 2 times the square root of 3 over 3. Square root of 3 times the square root of 3 is 3. So that's the secant. Now, to get the secant or the cosecant or the sine, we can use the Pythagorean identity. So that says the sine squared of x plus the cosine squared of x equals 1. And this applies to any quadrant. We are going to have the issue where we're going to take a square root, and it'll be plus or minus, and we'll have to use this information to figure out what the sign of the sine is. So remember, the sine is positive in the first quadrant and in the second quadrant, and it's negative in the third and fourth quadrant. So because our solution is in the third quadrant, we need the sign to be negative. So let's solve for the sine from the Pythagorean identity. So we get the sine squared equals 1 minus cosine squared, or the sine is equal to plus or minus the square root of 1 minus cosine squared. So we know what the cosine is. We just had it earlier. That's equal to the negative of the square root of 3 over 2. So the sine of x is plus or minus. And because we're in the third quadrant, the sine is going to be negative. So we're going to use the negative square root. So we could say Q3 is negative the square root of 1 minus cosine squared of x. So we get negative the square root of 1 minus the cosine, which is negative the square root of 3 over 2. We square that. So you get negative the square root of 1 minus, well, the squaring in the negative makes it positive. So we square the square root of 3, which is 3. We square 2, which is 4. So we get the negative the square root of 1/4. 1/4 minus 3/4 is 1/4. Take the square root of 1, you get 1. The square root of 4, you get 2. So the sign of x is negative 1/2. And then finally, you can use the reciprocal identity. So the cosecant of x is equal to negative 2. So the reciprocal of 1/2 is 2 over 1. 1 over 2 is 2 over 1. So you get the cosecant. So those are all the 6 trig functions. So the whole idea is if you're given 2 trig functions, you can get the reciprocal functions just by taking the reciprocal of the number, and then you can use the Pythagorean identity to find the other trig function. You use plus or minus depending upon what the signs of the original 2 functions were to find the coordinate, the quadrant. Okay, so that's the first group. So we'll do one more like that, and we'll make sure we don't do one that I'm giving you. So let's do number 7 in the book, which is secant of phi. Phi is just another Greek letter that we use to represent angles. So that's 3/2 secant, and the cosecant of phi is negative 3 times the square root of 5 over 5. Okay, so as we said, the first thing you do is you do the reciprocal identities, the reciprocal functions. So the cosine is 1 over the secant. So here we get 2/3 instead of 3/2. And the reciprocal of the sine, cosecant is a sine, so you get negative 5 divided by 3 times the square root of 5. But we have that square root of 5 in the denominator, so we're gonna multiply and divide by the square root of 5. So the numerator we get 5 times the square root of 5, and the denominator we get 3 times 5. Square root of 5 times the square root of 5 is 5. So these cancel out, and we end up with negative the square root of 5 over 3. And then finally the tangent. So the tangent of theta is just the sine of theta, or phi in this case. So the tangent of phi is the sine of phi over the cosine of phi. And so the sine is negative the square root of 5 over 3 divided by the cosine, which is 2 over 3. So instead of dividing by 2/3, we're going to multiply by 3/2. So you see the 3's cancel out, and we get negative the square root of 5 over 2. So that's the tangent of phi. And then you can find the cotangent of phi by taking the reciprocal. So we get, instead of the square root of 5 over 2, we get 2 over the square root of 5. The sign's the same, it's negative. And multiply and divide by the square root of 5, you get negative 2 square root of 5 over 5. And so in this case, you see, you don't have to make any decisions about which quadrant, what quadrant I am in. But I could kind of figure it out, right? So the cosine is positive. Here's my all students take calculus. So we have the sine, cosine, tangent. They're all positive in the first quadrant. The sine is positive in the second quadrant. Tangent is positive in the third quadrant. Cosine is positive in the fourth quadrant. And all the ones I haven't included are minus signs. So if we look at the first piece of information here, the cosine is positive, so that's going to be here and here. The sine is negative, cosine's negative, sine's negative, so that means it's here and here. So that means it has to be in the fourth quadrant, which means the tangent also has to be negative, which we didn't have to make any decisions. It came out automatically. So the identities we're using here are the reciprocal identities and the Pythagorean identities. Now the second group of problems, there's only one in the book, so I can't repeat that, so you'll just have to look at it and try to figure out what the heck's going on. I'm just looking through here. Actually, I think I'm having you do 15 through 20, so I could do 21 through 26, so why don't we do that? So what we have these three or these six functions, and they're not all just simple functions. So we got A is cosecant, B is tangent, C is sine squared, D is sine x tangent x, E is secant squared x, and F is secant squared x plus tangent squared x. And what we're given is 6 equations, and we're supposed to show that we can simplify these down to one of the 6 choices and match them up. So it's a matter of using the trig identities that we've learned, reciprocal identities, the Pythagorean identity, the cofactor identities, and what it is called, the odd-even identities, to make this look like one of these 6. So in this case, it looks like using a reciprocal identity would make sense. So the secant is 1 over the cosine. So that's a reciprocal identity. So then you have the sine over the cosine. That's a quotient identity. That's equal to the tangent of x. And are there any here that are the tangent of x? Well, yeah, this one. So that's B. So 21 matches up with B. Okay, let's do the next one, which is cosine squared x times secant squared x minus 1. Now typically if you have something squared plus or minus 1, that usually indicates to use a Pythagorean identity. So if we go back to the identity list and we look for a Pythagorean identity that involves secants, we see there's this identity. So you get 1 plus tangent squared x equals secant squared x. So you can see if I can manipulate this to be secant squared x minus 1. I just subtract 1 from both sides. So you can see that's the same, so I can substitute that in. So I get cosine squared x times tangent squared x. Then I can, so now I'm using this is the Pythagorean identity to substitute. So I get cosine squared x times. And then I can rewrite the tangent in the quotient identity. Tangent is sine over cosine, so the tangent squared is sine squared over cosine squared. So I cancel out the cosine. I'm left with sine squared x, and that looks like something that might be one of my choices, which it is. So this, the answer here is choice C. And you can see I'm underlining. So part of it, when you get further along, you can use process of elimination. Okay, next one is secant to the fourth minus tangent to the fourth x. So what is that equal to, and what one should I use? Well, this to me looks like if I factor this, and so it's kind of like x squared minus 1. That factors out as x plus 1 times x minus 1. So you take, because this is negative, I can alternate it to make the inner and outer terms disappear. So it would seem like it would be secant squared x plus tangent squared x times secant squared x minus tangent squared x. So if you multiply the first together, you get secant to the fourth. The inner and the outer cancel out because one's plus secant squared tangent squared, the other one's minus secant squared tangent squared. And if you multiply the last together, you get negative tangent to the fourth. So that looks pretty good. So now you can see that up here we had this trigonometric identity, 1 plus tangent squared equals secant squared. So I can take that same thing, and you can see secant squared minus tangent squared. So I'm going to just write it up here. If I take this same trig identity but subtract tangent squared from both sides, like that, and that matches up with secant squared x tangent squared x. So this part is 1. So what I'm left with is secant squared x plus tangent squared x, and that is this choice, secant squared x plus tangent squared x. So this corresponds to F, which I haven't used before. Okay, the next one we're doing is 24, which is cotangent x secant x. So there's no squared, so you're probably not going to use the Pythagorean identity. We could use the, try to write this in just sine and cosine. So the cotangent is the cosine of x divided by the sine of x. So that's a quotient identity. The secant is 1 over the cosine. That's the reciprocal identity. These cancel out to be 1. You get 1 over the sine. But 1 over the sine is the cosecant. That's probably one of my choices. There we go. The first one here. So this corresponds to A. Choice A. Again, which we haven't used yet, so that works out good. The next one they have is secant squared x minus 1 over sine squared x. So it's either going to be sine x, tangent x, or secant squared x. Those are my only two choices. Again, this looks like something I could use one of the Pythagorean identities. So if you go to the Pythagorean identity part, you get 1 plus tangent squared equals secant squared, or tangent squared equals secant squared minus 1. So just subtract 1 from both sides. So the numerator becomes tangent squared, and the denominator is sine squared. So then finally, we can then use the quotient identity. Sine squared x, sine over cosine is the tangent, so the sine divided by sine squared divided by the cosine squared is the tangent squared. And then I divide that by the sine, and you can see if I take the reciprocal of this, it's the same as multiplying by 1 divided by sine squared. So you get, what you'll end up with is 1 over cosine squared, which is, using the reciprocal identity, the secant squared. So that's that. That agrees with E. So this one becomes choice E. And so we know what the final answer is. We just have to prove that it is that. So the last choice here is I've got the cosine squared of pi over 2 minus x divided by cosine of x. So anytime you have these pi over 2's or pi's in there, that's probably one of those cofactor identities. So let's look on our, let me just add a page here and write down the one that looks most likely to work. So I've got cosine of pi. So if I look at that, cofunction identities, there's one involving the cosine. It says cosine of pi over 2 minus u equals the sine of u. So in our case, we're using x instead of u. So the numerator becomes, instead of the cosine squared of pi over 2 minus x, it becomes just the sine squared of x. And we divide by the cosine of x, because that's what's in the denominator. And then finally, we can rewrite this as the sine of x divided by the cosine of x times 1 over the sine over the cosine. So the sine squared I can break apart into two sines, and the sine over the cosine is the tangent. So I get the tangent of x times the sine of x, or switch the order, the sine of x times the tangent of x, which is d. So this is d. Okay, so that's, you can see I've used all the different kinds. The only thing I didn't use was the odd-even identities, and we don't use those too much. Okay, so you got one like that, except they're different functions, but the concept is the same. Okay, the next group says use the fundamental identities to simplify the expression. There's more than one correct answer, so they're not telling you what the answer could be. So you just have to do your best, and hopefully you get down to something that's simplified. So let me find one here. So let's say I've got the cosine of theta tangent of theta. So I'm just simplifying it. So this again looks like something that I can use the quotient identity to replace the tangent with the cosine divided by the sine. Cosine divided by cosine is 1. So this becomes the sine of theta, which is probably the only answer. Okay, next one. Let's see, let's do another one here. So we've got the cotangent of x divided by the cosecant of x. Again, there's nothing squared, so it's probably not going to be a Pythagorean identity. We do have something here that's defined using a quotient, which is the tangent and the cotangent. So the cotangent is the cosine divided by the sine, and the cosecant using the reciprocal identity is 1 over the sine. And again, you can, instead of dividing by 1 over the sine of x, we can take the reciprocal, which is not 1 over the sine, but this is sine over 1. Sines cancel out, and you get the cosine, and that's the answer for this case. Okay, let's do one more. Not one more, but some more. Let's say we have 1 over the tangent squared of x plus 1. So this is involving something squared plus or minus 1, so that looks like I could use one of the appropriate Pythagorean identities. And there is this 1 plus tangent squared x equals secant squared x. I've got tangent squared x plus 1, so it's the same thing. So I can replace that with the secant squared. And typically, if you can replace a fraction with just an expression, you want to do that. So we would use the reciprocal identity that 1 over the secant equals the cosine. So the answer would be cosine squared. And you can always check these by plotting the functions. And if they are match up completely, then you've got the answer. Got the correct answer. Okay, let's look at one more here. So let's say we have the cotangent of x sine of x plus tangent of x cosine of x. So again, anytime I see cotangent or tangent, I think of using the quotient identities. So the cotangent is cosine over the sine, and the tangent is the sine over the cosine. And you see what happens is this cancels out with that, that cancels out with that, and we're just left with the cosine of x plus the sine of x. And that's pretty much all she wrote there. You know, simplification usually means if you have a rational expression, you can make it into a non-rational expression. Or if you've got 4 terms, you can simplify it down to 2 terms. That's what would happen in this particular case. We start out with cotangent, sine, tangent, cosine, but we ended up with cosine and sine. Okay, and the last group, I think, no, it's not necessarily the last group. The next section is using factoring. We kind of did that, I thought, earlier. So there's just more examples of factoring. So let's say we have the sine squared of x, secant squared of x minus sine of x, sine squared of x. So you see we have this common term, which is the sine squared. So we can factor that out. Factoring it out means we take the terms, write the factor, and then divide each of these by that factor. So if we divide this by the sine squared, we're left with the secant squared. And if we divide this by sine squared, we're left with -1. That in itself is not that much of a simplification, but remember we have this Pythagorean identity involving the tangent and the secant. So if I subtract 1 from both sides, I get that. So I can replace secant squared x minus 1 with tangent. So I get sine squared times tangent squared. So that is simplified. But we can go one step further because the tangent, not sure if we go that much further, if it's that much better, because you'd have, if I were to rewrite this as tangent squared is sine squared over cosine squared, I'd end up with sine to the 4th x over cosine to the 4th, or squared x. So whether these are any better than the others, this one doesn't have a quotient. This one doesn't have tangent, so it's only a function of sine and cosine. So yeah, I don't know. Wonder what let's see what the book did on that one. Which one they considered to be sufficient. So that's number 47. 5.1. Should be pausing this, but by the time I pause it, I will have found it. Actually, I am going to pause it. Okay, they did the one here. They didn't go the extra way, which I didn't think they would. Okay. Let's do this one. Secant squared x minus 1 divided by secant x minus 1. So what you can do in this case is you could factor the numerator. You might think of replacing this with the tangent squared, but that really wouldn't help you a whole lot. But if you'd factored this as secant of x minus 1 times the secant of x plus 1, and you divide by secant of x minus 1, you can see that these are the same, and so you can replace it. So you get rid of the rational function, and so that one looks pretty good. Okay, let's do another one here. So let's say you have secant cubed x minus secant squared x minus secant x plus 1. So that's a little difficult, but what you have to do is think of it as this: x cubed minus x squared minus x plus 1. So how would we factor that? Well, we probably use synthetic division. So you'd have 1 minus 1 minus 1, 1. And let's say x equals 1. Let's try that. So you bring that down. 1 times 1 is 1. Negative 1 plus 1 is 0. 0 times 1 is 0. Negative 1 plus 0 is negative 1. 1 times negative 1 is negative 1. So you get that. So what that says is this can be factored as x minus 1, because the corresponding factor to x equals 1 is x minus 1. And then you're left with x squared minus 1, which you could factor this one because it's going to be just x minus 1 times x plus 1, because the inner and outer will cancel out. So what we can do is we can just substitute in secant for this. So you have, but actually I think we're going to use this because we can, I'll show you in a second why. So you get secant of x minus 1 times secant squared of x minus 1. But secant squared x minus 1, we just looked at that. That's equal to the tangent squared of x. And I think one more thing you could do is you could write this as secant of x is 1 over the cosine of x, and tangent is sine squared over cosine squared. I think this might be the answer. So let me just pause and look in the back of the book. Okay, that's actually the final answer. I didn't think, sometimes you have to realize that going further is not really helping your situation. So again, we went from 4 terms down to less terms, so it is a simplification. So that's the group that involves using factoring to rewrite the things. Okay, we skip over a section here, and we've got this next group of problems. So let me just show you what it looks like, and then we can talk about it. So you get 1 over 1 plus cosine x minus plus 1 over 1 minus cosine of x. So you've got these two rational functions. The first thing you think about doing is combining these two, and your common denominator would have to be the product of these two things. So if we multiplied the first term by the denominator of the second, you'd end up with 1 times 1 minus cosine x. And when you multiply them together here, you'll get 1 minus cosine squared x. So this times that, you get 1, the inner and outer cancel out, you get positive cosine x times negative cosine x, which gives you negative cosine x squared. And then the second term, you're going to multiply by 1 plus cosine of x in both the numerator and the denominator to get the same denominator. So I multiplied this by 1 minus cosine x over 1 minus cosine x. This is the same by 1 plus cosine of x over 1 plus cosine of x. And now I have the same common denominator, and I add the exponents, the numerators together, so you have 1 minus cosine plus 1 plus cosine. So the cosines cancel out, and you get 1 divided by 1 minus cosine squared of x. And you think, oh, maybe I'm done. But remember the Pythagorean identity involving the cosine and the sine is this. So the sine squared of x is equal to 1 minus cosine squared of x. So I can replace that with 1 over the sine squared of x, which is, using the reciprocal identity, 1 over the sine is the cosecant, so I get cosecant squared x. So that's my final answer. Let's just show you one more here. There's only 4 of these problems, so I'm doing 2 of them, and you got 2 other ones for homework. Let's think about how we would handle this. So I'm looking at that and I'm thinking, okay, what am I going to do? Well, again, you could come up with a common denominator, and which would be the product of these two. So you'd have 1 plus sine x times cosine of x. That's the common denominator. So I'd have to take this fraction and multiply by the second denominator. Multiply that by the first numerator. So I'd get cosine x times cosine x, which would be cosine squared x. Here I'd have 1 plus sine x times 1 plus sine x. Well, you'll get 1 plus, so that's 1 times 1. Then you get sine x times 1 plus sine x times 1, so that's 2 sine x. And then I get sine x times sine x, which is sine squared x. So at first that doesn't look too good, but I say, oh, okay, here we've got cosine x, here I've got cosine squared x, sine squared x. These two equal 1 from this Pythagorean identity that I used earlier. So this is 1, so I take 1 plus 1 is 2, so I get 2 plus the remaining term is 2 sine x over 1 plus sine x divided by cosine x. Okay. But if I factor out a 2 out of the 2 terms in the numerator, I'll get 1 plus sine x, which happens to be one of the terms in the denominator. So these cancel out, and I get 2 over the cosine of x. But again, I don't like stuff in the denominator if I can help it, so the reciprocal of the cosine is the secant. So that whole thing just reduces down to 2 secant x. Okay. Okay, then you are asked to use a graphing utility to verify that these functions are one of the 6 trigonometric functions. So you have to, well, you could prove it. Actually, it does ask you to verify it algebraically, so we're going to do it both ways. So you've got something like here, which is, so you got the cosine of x times the cotangent of x plus the sine of x. So that's got to be one of the 6 trig functions: sine, cosine, tangent, secant, cosecant, cotangent. So if you want to verify this thing graphically, what you would do is you'd plot the function, which is cosine of x, cotangent of x, I think that's what it was, plus sine x. And you plot it between 0 and 2 pi, and it looks like that. So that is the that's the cosecant function. It's definitely not the sine or the cosine. And the secant function has a value of 1 when x equals 0. This has a value of 1 when x equals pi over 2, so it's definitely the cosecant. We talked about that in chapter 4, section 6, what the kind of general shape of these curves are. So our supposition from the graph is that it's equal to the cosecant of x. So let's see if we can figure this one out. So if we got cosine, cotangent is cosine over sine. So that's the quotient identity. So you end up with cosine squared x over sine x plus sine x. So if you have two numbers, two parts, you want to combine them together. So I'm going to multiply the second term by the sine of x. I'm going to divide by the sine of x, and that's to get the same denominator. So from the first term I'll get cosine squared. Second term I'll get sine squared, and I divide the whole thing by the common denominator of the sine of x. But the cosine squared plus the sine squared equals 1, so I get 1 over the sine of x, which is equal to the cosecant of x, which is what we showed graphically. So that's how those work. And so you got two problems like that. And then the last one is this trigonometric substitution, and this has use in second semester calculus. So what you've done, what happens is you are given some kind of a trigonometric situation here. So you have this square root of 9 minus x squared, and the substitution is that x equals 3 cosine theta. So what we want to do is substitute this into the square root expression, and we want to rewrite this in terms of trig functions, because it turns out that if I can reduce this down to something simpler, I can probably deal with it in calculus. So what we do is we put in, for x, we put in the substitution, which is 3 cosine theta, and we square that. And then we multiply out this, so 3 squared is 9, which not so coincidentally is what we have in the first term. And then you can factor out the 9, so you have 1 minus cosine. It's 9 times 1 minus cosine squared theta. The square root of 9 is 3, so you have 3 times the square root of 1 minus cosine squared theta. But the Pythagorean identity says that the square 1 minus cosine theta is equal to the sine squared of theta, and the square root of the sine squared is the sine. And so that's the final answer. So this somewhat complex algebraic expression using this substitution comes out with this pretty simple trigonometric expression. So let's do another one here. So if you got the square root of x squared plus 25, using the substitution x equals 5 tangent of theta. So again, plug in for x, so we have 5 tangent of theta quantity squared instead of x squared. We have 25 But if we square 5, we get 25. If we square tangent, we get tangent squared. Then we add 25 to it, our second term. And again, we can factor out the 25. So we have 25 tangent squared theta plus 1. Square root of 25 is 5. Here we get the square root of secant squared. So tangent squared theta plus 1 using the Pythagorean identity is equal to secant squared. And then the square root of the secant squared is just the secant. So one thing when you get to calculus is that you'll find there's this tendency to have cosine and the sine kind of attached, and the secant and the tangent kind of attached to each other. You see one, you see the other. And the last problems just ask you to use a graphing utility to prove or to show when these functions are true. So I've got, here's an example, cosine of theta equals square root, or negative the square root of 1 minus sine squared theta. So there's two ways of doing this. You could plot y equals cosine theta and y equals, or x, because that's what my graphing program is going to do, and one that's y equals negative the square root of 1 minus sine squared of x, and see where they're the same curve. Or you could plot the function y equals the cosine of theta plus the square root of 1 minus sine squared theta. And where y equals 0, when y equals 0, this is true. So what I did is I moved this term on the right-hand side to the left-hand side so it became positive. And then I said this is my function. And that's the way I'm going to do it. And you'll see what happens. So let's minimize this thing. And I'm going to go from 0 to 2 pi. So we have the cosine of x instead of theta plus the square root of 1 minus sine of x quantity squared. Close the parentheses for the sine of the square root. And I plot that and I get that. Okay, so you can see between pi over 2 and 3 pi over 2 that this function equals 0, and that's the same interval over which this equality holds true. So the answer is the interval is from pi over 2 to 3 pi over 2 is when this is true. Okay.